Hey everybody, today's video is going to be about geometric sequences. So we had arithmetic sequences, which were sequences where they had a common difference. You add the same amount every time. In a geometric sequence, we have what's called a common ratio. We're going to multiply by the same amount every time to get to the next term. So right away, we'll just jump off with like the definition of it. If we take our first term, a1, and multiply it by r every time, we get this pattern, a1 times r, a1 times r squared, a1 times r third. And so we get a formula, an explicit formula, for the nth term of a geometric sequence is a sub n equals a sub 1 times r to the n minus 1, where r is the common ratio. So we got kind of a lot of examples here, so I've got some stuff worked through already. If you need to pause and at any point, make sure you do that. So example 1 here, we're given the sequence negative 144, 36, negative 9, 2.25, and our job is to write the nth term. First, we got to actually confirm that it's geometric. So to do that, you can see what I've done is I've made a little division problem. So I'm trying to see how did I get from negative 144 to 36? I had to multiply by something. So to figure out what that something was, I divide. I do a term divided by the one before it. 36 divided by negative 144, and that turns out to be negative 1/4. And I can test the next pair. Does negative 9 divided by 36, does that also equal negative 1/4? And it does. And 2.25 out of negative 9 is also negative 1/4. So what I've done is I've found what is the common ratio. What am I multiplying by to get to the next? If I take 144 times negative 1/4, negative 144 times negative 1/4 gives me positive 36. Positive 36 times negative 1/4 gives me negative 9, etc. So that's my common ratio. My first term is right there, negative 144. So I get my geometric sequence nth term formula is a sub n equals first term, negative 144, times the common ratio, negative 1/4, raised to the n minus 1. Okay, if I asked you to find the 12th term, we could do that just by plugging in 12 there. And this would be probably a calculator problem if I were to ask you the 12th term, because we'd be raising negative 1/4 to the 11th power. In example 2, we've got, is this sequence geometric? So it asks us that outright. Is it geometric? So we got some crazy decimals here. That's okay. Same process. Take a term, divide it by the one before it, and see if we get the same answer every time. So take out your calculators and divide 17.64 by 8.4 and see what you get. You should get 2.1. And if we do the same thing, again, like that doesn't confirm this is geometric just because this times that, this times 2.1 equals 17.64, doesn't mean the next one works. So we got to check all of them. So 37.044 divided by 17.64, yep, that's 2.1 also. And if we did the last one, we'd find that it's 2.1. So we now know our common ratio is 2.1, so I can make my nth term 8.4 times 2.1 raised to the n minus 1. Okay, next up, we can get a little trickier. This time, and we did this with arithmetic too, I give you two terms of a geometric sequence that are not consecutive. And it's important we are told it's geometric, so we know there will be a common ratio connecting these. So we have the third term is 75/16, and the sixth term is 9,375 over 1024. All right, there's a few different ways to approach this problem. I'm going to show you one of them here, where we basically set up our a sub n equals a sub 1 r n minus 1 formula for both of those terms. So I know the third term, so I'm plugging in 3 for n, would be this here, 75 over 16 equals a sub 1 times r to the 3 minus 1. And I can do the same thing with the big fraction there of 93 375 over 1024. And now basically I have a system. A1 and R are my two variables. So one way we could solve this system is basically dividing each equation by the other. In other words, I'm going to write the first equation, and I'm going to divide the second equation by the first equation. So I'm going to take that, and I'm going to write underneath it 75 over 16, and on the right side I'm going to divide by A1 times R to the, so 3 minus 1 is 2, R squared, 6 minus 1 is 5, if we wanted to fix that there. And so on the left side, we get kind of a complex fraction, but on the right side, the a's cancel out. The a1's the first term, and I'm going to get r to the third, because I have r to the fifth over r squared. So I'm going to get r to the third equals 9375 over 1024 times the reciprocal, 16 over 75. So if I wanted to solve for r, it would be the cube root of all of that. And so you could type that in your calculator. I'm not going to rewrite all that. We will find out that r is the nice fraction 5/4. All that. R is 5/4. All right. Now, let's be thoughtful here. I now know my common ratio is 5/4. And I guess I didn't copy down the part of the problem that actually asks us what to do. It's supposed to say find a sub 5, or the fifth term. So what I could do is kind of finish off a system the way we normally finish off a system, which would be plugging 5/4 back in. 75 over 16 equals a1 times 5/4 squared, and we could solve for a1, and when you do that, we find out that the first term is 3. Okay, kind of draw a path here. That's what we did. And now that I know that I have 3 as my first term, I could go back up here and say a sub n equals 3 times 5/4 to the n minus 1, and then plug in 5 to get the fifth term. And when you do that, we get 1875 over 256. Okay, that works great, and you can do it that way. But if you think about it, we knew a6. And we wanted to find a5. a6 was 9375 over 1024. And I know that to get a6, I had to multiply by 5 over 4. So if I wanted to find a5, couldn't I take that and just divide by 5 over 4? And you could. And so if you did that, you would get the same answer. So that's another, maybe a more creative way of solving that one. We still had to go through that first process to find r in the first place. Okay, so now we're going to talk about partial sums of geometric sequences. I have this here because I really like this proof. It's kind of a neat little proof of how we get the formula for the partial sum of a geometric sequence. So I'm going to try to talk through it quickly. You don't have to write it down, but our partial sum is the first sum of the first n terms. Okay, so if I have a geometric series sequence, it would be a1 plus a1r plus a1r squared all the way up till we get till the last term. Well, if we're adding up n terms, the last term is a1r n minus 1. So we have that. So the way we do this is we take that partial sum and we actually multiply it by r. So I'm going to take a1 times r, which would get me a1r. I'm going to take a1r times r and get a1r squared. And everything just kind of bumps over. So we have this equation for s sub n, and we have the new equation for r times s sub n. Well, you notice those all line up. And if we subtracted, every single one of those would cancel out in the middle, except for the first and the last. So I would get s sub n minus r times s sub n equals a1 plus a times r to the n. And so we can do a little factoring on each side to get S sub n factored out and A1 factored out, and then we divide, and we get this nice formula there. And I think that's pretty cool. So looking at that a little more neatly, here's our formula for the partial sum of a geometric sequence. It involves the first term times 1 minus r to the n on the top, and 1 minus r on the bottom of the fraction. And we just saw above how to prove that. All right. Example 4. Okay. Find the sum. We got 1 minus 1.5 plus 2.25 minus, and the pattern continues until we get till 25 point blah. All right. So it's going to be geometric. Problem will probably tell you this one's geometric, but we find the ratio negative 1.5 divided by 1 is just negative 1.5. So that's what the ratio is. I know the first term is 1. I know the last term is the 25.6 whatever. I need a 5 in there. But I don't know the n for that, because if I'm going to use my sum formula, I need how many terms it is, because we've got 1 from the first term, 1 minus r, negative 1.5, but I don't know n, and that's what I have to find. So I'm going to solve for n, and when we set up our equation here to solve for n, we actually run into like a little bit of a problem. And so let's take a look. We're going to use our just a sub n formula, but I know that I know the nth term is the 25.628 number equals, so a sub n equals a sub 1 times r, negative 1.5 to the n minus 1. Okay, well, if you think about how we would solve this equation here, we would use logs, right? And I would log both sides. But hopefully you either maybe are recognizing a problem here, or once I mention it, you'd be like, oh yeah, that is a problem. You can't take the log of a negative number, okay? So for this solving of n, like whether or not this alternates or not, n would still be the same. So we can make this positive for the solving part, even though r is negative. So we're going to go through, we're going to log both sides. So I'm going to get natural log of 25.628 equals n minus 1. You bring the exponent down, natural log of 1.5. And then you divide it to the other side. So we get n minus 1 equals natural log of 25.628 over natural log of 1.5. And when you do that all on your calculator, you're going to find that n equals 9. Great, now we know n. So I can go back to my S sub n formula, and I'm actually doing S sub 9 equals 1 times 1 minus, and this time we do need the negative, 1.5 to the 9th, all over 1 plus 1.5 because of the minus negative, and sum that out on your calculator. You get 15.777 34375. Great. Woohoo. Okay, that's what it equals. Okay, in the interest of time, I'm gonna kind of skip through this one real quick. But we've got our summation notation, and the key is recognizing this is geometric here. It's our formula, a sub 1, r, n minus 1. So you can find your first term by plugging in 1. Find your ratios right there. And we know n, the number of terms we're adding up is going to be 10, because we're going all the way from 1 to 10. So you plug in the formula. This is what you get in a calculator. Pause it if you need to. Moving on. We are going to go to talk about infinite series, right? And we get into some kind of funky vocab here. And an infinite series would be a sum that we added up forever. Instead of stopping at a certain point, we'd add it up forever. Okay? And we have kind of two different things that can happen. Either it gets really close to some finite number, and if that happens, we say it converges, or it doesn't get to a finite number, and then we say it diverges. What am I talking about? Well, look down here bottom left at this example. If I added up 1 plus 2 plus 4 plus 8 plus 16 plus kept going forever, that's just going to keep getting bigger and bigger and bigger. It's not going to converge on a single sum. It's going to diverge. So that we call a divergent series, infinite series. But this one, 1 plus a half plus 1/4 plus 1/8 plus 1/16, every time I'm adding something smaller and smaller and smaller. So we're going to see that this would actually converge on a number, okay? And here's where the vocabulary gets kind of picky, because we're going to sort of say that the sum is that number. For something that converges, essentially what you're saying that as the n value goes to infinity, as the n value gets really, really big, the sum approaches this number s. And we're going to call that s the sum of the infinite series. Okay? But if you look closely at the wording here, if s sub n gets close to a finite number s, we say that it converges, and that number s is called the sum. So if you want to get really technical about it, it doesn't necessarily equal that sum, but it's getting really, really, really close to it, so we kind of say it equals that sum. All right, infinity is kind of a weird thing. So anyway, real quick, if we have, what's happening here is this is a ratio that's less than or equal to, or not less than or equal to, less than 1. Okay, a ratio that's less than 1 will converge because we're going to get smaller and smaller every time. So if you look at our formula up here, if r is less than 1, some number less than 1 to the nth power, as I let n get really, really big, that's going to go to 0. Okay, and so we end up with this nice infinite sum formula as a1 over 1 minus r. And we're going to actually see that on the next page. Okay, so if r is less than 1, and the absolute value means it could be positive, could be negative, as long as it's between -1 and 1, and then we get that the infinite geometric series will converge and have this sum. If r is bigger than or equal to 1, we say the series diverges. Okay. What's nice is these problems are very easy. So if you look at this, 3 plus 1 plus 1/3 plus 1/9, we can figure out the sum that this converges to, because r is 1/3, so we know it converges, and a1 is 3. So I'm going to say the infinite sum is equal to 3 over a1, looking at my formula there, a1 over 1 minus 1/3, 1 minus r. So that's 3 over 2/3, which is 9 over 2. And so we say that the sum of that infinite series is 9 over 2. And that's the number that this would get really, 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 really close to. If you went on your calculator and started typing in and went 1 over plus 1 over 9 plus 1 over 27 plus etc., 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 you would see you're getting really close to 4.5. Okay, couple last quick problems here. So example 7 here, write 0.27 repeating as a fraction. And what we can do to come up with this is to recognize that 0.27 repeating could be written as an infinite series. How does that work? Well, the first 0.27 is 27/100ths. And then that second 27 is really 27 10,000ths, right? Tenths, hundredths, thousandths, 10,000ths. So 27 10,000th plus 27 1 millionths, etc. Right? And so I see that I have a first term of 27 over 100. And my common ratio, the top is multiplied by 1 every time. And I'm multiplying by 10 or 100 on the bottom every time. So my ratio is 1/100th. So that's really an infinite series where the first term, so 27 over 100, divided by 1 minus the ratio, 1 over 100. And if you did that, you get 27 over 100 times, this is going to be 99/100ths, so 100 over 99. Those 100s cancel out, so you get 27 over 99. And if you plug that in your calculator, you would see we get 27.27 repeating. Okay, that's all. Thank you for watching.